you for the nice introduction. As she said, I'm going to present to you my work about photosensitivity in Cumulene-based transistors. So we will start off with an introduction on Cumulene, since I expect that at least some of you are not completely familiar with this category of materials. Then we will tackle a particular Cumulene, 3pH, in regard to its stability. Then we will focus on its photosensitivity specifically, and then our strategy to try and counteract this effect. So this is a Cumulene. It is a molecule with a highly conjugated sp carbon backbone and 4 termination groups. And it is the finite version of the actual sp carbon allotrope carbine, which has actually been predicted to have outstanding properties spanning from the mechanical and thermal ones to also electronic ones, which are what interests us all. So cumulenic molecules in particular are semiconductors, and those are highly tunable semiconductors. You can achieve a wide variety of electronic behaviors through a careful engineering of the molecule itself. In addition, those are all solution processable materials. So in the context of organic electronics, those are considered very interesting materials. Here we have in particular 3pH, which is the reference molecule for the whole class, thanks to its good behavior in organic field effect transistors. And it also displays an overall good stability overall again. So let's just focus a bit on the device itself. This material was optimized for organic field effect transistor just a couple of years ago. So the study is quite recent. Although these materials reveal to be quite promising, it has a very good close to ideality behavior, as you can see, with reliability factors up to 0.97 also, in general, as an average 0.90, let's say, a good threshold voltage, a good on-off ratio, a good field effect mobility. So overall good performance. The point is that for having actual applications, high performance are not enough. You need a material that is reliable, so stable. So actually, 3pH in particular has a good stability, I said. In particular, it is very well stable in air. We store typically 3pH powder in air again, and it can last up to a few years. I have 3 years old powders, which are perfectly fine, no damage of degradation at all. Also, solutions are quite long lasting. I tried and fabricated transistor from 4 or even 3 months old solutions. Of course, we will have a rise in the occurrence due to a higher absorption of oxygen in the solution. That's to be expected, but other than that, the devices are perfectly fine. As for operational stability, again, 3pH behaves quite well. As you can see, it has a very good behavior in both nitrogen and in air atmosphere. Expectedly, off currents in air are much higher due to oxygen doping, of course. But overall, after over a period of time of 12 hours of consistent measurements, we have a very good on-off ratio increase and a very small linear mobility decrease. So overall, good operational stability. We have a condition where 3pH is not so stable, and that is underlight, unfortunately. So this is what happens to a Cumulenic, in particular 3pH film, after 60 seconds under regular optical microscope light. Signs of degradation are quite evident, so the crystalline structure is permanently degraded after this exposure. To have a better idea of how much those are photosensitive, we set up this experiment with a very weak and focused light source as a probe, and then we shine on thin film LEDs with different wavelengths, one wavelength at a time. And you can see that the signature peak of this molecule corresponding to its homolumo transition is bleached already in the visible range. Those are 30 seconds exposure, so a relatively short time to already see large effects of photodegradation. The issue here is that most human activities actually take place under light, so this is an issue that we need to solve if we want to hope for actual applications for Cumulenes. So before getting to our strategy to try and fix this issue, let's discuss a little bit what kind of devices we're talking about. Those are top gate bottom contact devices with evaporated gold contacts. The semiconductor was barcoded into a very homogeneous and crystalline thin film. As a dielectric, we pick Parylene C. And then the optimized reported in literature device employs a thin, transparent layer of PSS inkjet printed directly on top of the channel area. And this is what happens when such a device is measured under light. You can see that straight away we have a decrease in the current and a definite threshold shift. Not only that, a huge hysteresis is formed, and all these effects seem to be permanent even after a long recovery. Of course, again, we have also a decrease in the off current, so probably part of this shift in the threshold voltage is also due to oxygen release, so a de-doping effect, but most of it is again the effect of light. So our strategy to counteract this effect was replacing the transparent PSS gate with an opaque activated carbon gate. The idea was to block out light, physically block out light from the channel area. And as you can see, this is exactly what happens. Just a clarification, under 300 nanometers, it is difficult to understand the contribution of the gate since the measurements were done on samples deposited on Corning glass that of course absorbs UV light. So it's difficult to understand what happens there, but from 300 nanometers up until, again, the infrared, definitely the activated carbon is a better shield than PSS. So the deposition of this new gate was quite straightforward. We simply spray coated through a shadow mask directly on the channel area. So this technique doesn't really require any fancy equipment, just an airbrush. And actually the ink itself is non-toxic. It is edible, actually. So overall is a very accessible, low effort technique to have. And it's an effective one because as you can see, those devices under the very same light cycles as before are quite stable. The only difference that we see is a shift in the threshold and a decrease in the off current. But then again, this measurement takes place in nitrogen atmosphere while the fabrication of the devices is made in air. So it is consistent with a de-doping effect from oxygen. This is a comparison for saturation field effect mobilities from between the two different kinds of devices. P.PSS is superior at SAR for sure. That's probably due to lower sheet resistance. The issue here is that, of course, it's not consistent throughout the experiment. Not only that, I should point out that as soon as light is shined upon the sample, we have a loss in ideality of the device. So even the extraction of the mobility is not so consistent and reliable for the P.PSS devices after the light is applied. While again, as we go back a little bit, we can see that the activated carbon gate device is perfectly fine. Nothing too weird about it. So here we have the mean values extracted from all the samples that were measured in this experiment. On-off ratio doesn't change so much between P.PSS and activated carbon, but saturation, field effect mobility, and also the threshold voltage changed quite a bit. Activated carbon seems to be quite consistent, while the P.PSS has a large decrease in the performance. So just to conclude, we have seen a few of the features of 3pH devices. We have gone through some of its stability features again, and then I presented to you a possible strategy, not only to protect cumulins from light, but also any other potentially organic photosensitive material, which might have high potentiality in under other conditions. Also, aside from photosensitivity, this is a very quick and low effort way to gauge devices. So it might be an asset for organic electronics, hopefully, or something like that. And with that, I thank all the people that collaborated with me on this project and on this paper, all my research group. And I thank you all for your attention. If you have any questions, I'm here.